So this is NCCER Instrumentation 2, Module 1. So measuring temperature. My first highlight is the first sentence on the page, and it's an online test question. When two objects make thermal heat contact, the object with the higher temperature cools. The cooler object cools as the cooler object becomes warmer, until a point it is finally reached where no change occurs. At this point, the two objects are said to be in thermal equilibrium with each other. Next paragraph, first sentence is highlighted. In 1724, Gabriel Fahrenheit developed a system that used mercury as a reference liquid to measure temperature. Temperature scales. I've got kind of a weird online test question. It's the 110 in temperature scale, second paragraph, first sentence. The Fahrenheit scale is commonly used for industrial measurements in the United States, and that goes along with the fifth paragraph, second sentence. The Celsius scale is also commonly used in industrial temperature measurement. Fahrenheit's used in the United States. Celsius is used most other places in the world. Everybody know how many countries like where Fahrenheit's used? I don't know who uses it. What's our standard called? Metric.
Imperial.
Huh?
Imperial.
Imperial. You know how many countries use the imperial standard? 4. The rat. Can you name one other one? Yeah.
No.
Myanmar, and I think it's a Middle Eastern country. I think it's not Saudi Arabia. I have to look it back up, but it's like Siberia, I think. Siberia, Myanmar, United States. Random. Wish we used metric. But both of those together are an online test question. Just need to know where you use them. And then in between those, I have another highlight. So the paragraph that starts with refer to figure 1, I've got the second sentence highlighted. Note that both Fahrenheit and the Rankine scale show 180 degrees between freezing and boiling points of water. They push that quite a bit in these chapters. If you look up on the board, you can see Fahrenheit and Rankine. So freezing point of Fahrenheit is 32, 212 is the boiling point, 180 degrees difference. Rankine, 492 to 672, 180 degrees. Celsius and Kelvin are also the same. 0 to 100, and then 273 to 373. They want you to, like, in your mind somehow you need to pair those up, and you need to have Fahrenheit you're going to know. If you can remember that the boiling point is 212, and it goes along with Rankine, you'll know that 180 degrees difference. Celsius, same thing, it's pretty easy. 0 is freezing, 100 is boiling. Just pair that with Kelvin. Last paragraph in 110, third sentence. Note in figure 1 that the Celsius and Kelvin scales each show there are 100 degrees between freezing and boiling points of water. Page 2. I've got both of the equations highlighted. So degrees Fahrenheit equals 1.8 times degrees Celsius plus 32. And then degrees Celsius equals degrees Fahrenheit minus 32 over 1.8. So they go through. You guys feel comfortable going back and forth on those, just plugging in Fahrenheit, Celsius? Alright, I'll work through one whenever we do review stuff, but we're going to push those quite a bit. Like I've got 4 questions that come off of those, just 2 highlights. Moving on to page 3, temperature measuring devices. So we kind of talked about this a little bit. Actually, no, we didn't. Thinking about a different class. Bimetallic thermometers. Second paragraph in 121 is an online test question. Second paragraph in 121 is an online test question. To calibrate a bimetallic thermometer, immerse in cold water bath that has a known temperature. Once the temperature is measured by the thermometer reaches the known temperature of the bath, adjust the pointer on the thermometer's scale to match. We talked maybe a little bit about bimetallic overloads, and it kind of works the same. Like remember the overloads can you have I think that was like copper and nickel, and they expand at different rates, so when they heat up they bend one way or another. This is kind of the same thing, except if you see the bottom, well, I don't have a picture, but if you see the bimetallic thermometer at the bottom, they kind of have a helical spiral going down. That's two metals that are back to back, and as they warm up or cool off, they expand in a known rate that's going to turn that dial and tell you what the temperature is. Pretty, you think if you actually think about that, it's impressive that people came up with this crap, but it's for as accurate as those are, that's a very simple measuring device. 1, 2, 2. I've got 3 questions that come out of the first 2 sentences in 1, 2, 2. A thermocouple is a device that works on the principle that when 2 dissimilar metals are in contact with one another, they produce a measurable potential or voltage. Separate highlight kind of as the temperature changes, the voltage also changes. A couple things to note with thermocouples. A lot of times you have to add an amplifier to be able to read the voltage, and you also have to have a changing temperature. If I just I've heated up some of the stuff that's out there and just try to take a straight millivolt reading on a thermocouple, and it doesn't read anything. But if you have it on there as it's going up or down, that's when it's going to show a difference. But if you flip over to page 4, you can see this picture on the board. So this is a thermocouple. Just know, I'm sure it's a highlight somewhere, but they have different colors mean different things. On a thermocouple, the red wire is always negative. It's very important, to be thermocouples work on voltage, so it's very important to have the polarity right. So every thermocouple is going to have a red wire, and that's always going to go to the negative, and then the other wire is going to go to the positive. The other wire is indicative of what type of thermocouple it is. So you're going to have a question come out of table 1, you got the type J, K, and T, which I think are probably the most common, and you can see the metals that are inside of them, like iron and constant stand. I don't know. So if it had a white conductor, you would know that's type J. This one up on the board has a yellow conductor, so we know that's a type K. Does that make sense? You also have, if you look in the bottom left, you have thermal wells. So the end.
We've done taken more highlights on the first page than we did all the last 2 chapters. This is about to suck.
I was watching, I finally have the video slow. Thanks. Okay. 5 seconds. Just trying to do it.
Yeah.
So a lot of if you guys are buying a meter, I would recommend buying one that can take temperature readings, especially even for personal use, but definitely in the home or something like that. I really like besides. Well, this does read capacitance. I really like these meters. For $80, these are nice meters. But you can have, I'm going to pass this around, and you're going to be able to see the picture that's on the ball on the board. You can see the ball on the end, that welded junction. But looking down at the bottom of this, I can see this is a type K. So if I strip the cloth insulation off the side of this, I should see what's K?
Yellow and red.
I should see that inside of this. But where this isn't just doing stuff at the house and whatnot, if you ever have an oven, mom bakes something and burns it or something like that, and she said like that's what I always cook it at. Like you can actually like stick this in the oven and see what the actual temperature is, and then most ovens have like you'd have to go in on like I've gone on Google and see how to get into like the programming of the oven, and you can do like a calibrated oven essentially. Like you can just like up it a few degrees or lower it. So I'm gonna pass this around, but just so y'all can see like the welded joint at the end. But take your fingers and like rub them on the create some friction and stuff like that, and see how the temperature and stuff goes up. But take a look at the end and see how the two metals are joined together on the end, like the two super small.
Big tube, that'd be perfect.
I don't have any other highlights on page 4, but it is. These are super important because thermocouples and RTDs are used everywhere for temperature detection because they are so simple. 2 wires. Usually you have to take that into like some type of thermocouple reader because the signals are so small. But really they're small, cheap, but pretty rugged pieces of equipment. The thermal wells in the bottom left of page 4, I don't have a highlight in that, but that's what's on the end of this thermal well. But that's what, like if you're heating up a tank or something like that, that's what actually goes inside the tank, and then this welded junction slides inside of that. And then you can see a full thermocouple or a thermal well up at the top of page 5. There's your board. There are, I think Instrumentation 3, when we go through temperature stuff, like they have a scale. This one doesn't have a scale in it, but there's certain thermocouples that work, that have range. Like if you see the temperature range of the 3 types, like obviously you want to pick one. You want to pick one that's closest to the center of your range. Like you don't want to pick a thermocouple that's all the way on one side. Like if I was measuring temperatures up to 1300 degrees, I wouldn't pick a type J. I would pick a type K so that it's more in the middle. But if I was just measuring like 100, like I don't know, 200 to 400 degrees, I wouldn't want to pick, like, it seems like why wouldn't you just pick K all the time? Because the range encompasses everything. With a type K, you don't get as big of a millivolt signal as you do with like a type J, so it's a lot harder to read, it's a lot harder to use than a type J. So that's all you want to look at whenever you're picking out stuff. Nothing else highlighted on page 5, but you do need to know. Let me just set it on there anywhere. 1, 2, 3. You need to know that a resistance temperature detector is an RTD. When I say RTD, I mean resistance temperature detector. Flipping over to page 6. I have this picture highlighted as an online test question. So figure 6 on page 6 is an online test question. You need to know, like I think they're just going to show a picture and say, what is this? You need to know that that is an RTD. It's very easy to tell the difference between a thermocouple and an RTD because the thermocouple has 3 wires. No, thermocouple has 2 wires, RTD has 3 wires. They work basically the same way except for an RTD changes resistance based on temperature where a thermocouple changes voltage. Thermistors 1, 2, 4. Top right of page 6. That first started paragraph, second sentence is an online test question. I have a lot of online test questions in this chapter. Second sentence, positive temperature coefficient, PTC, thermistors increase the resistance with the rise in temperature. Online test question. Last paragraph before 125. First sentence is an online test question. At high temperatures, a thermistor is susceptible to drifting out of its specified tolerances and becoming permanently inaccurate. You can see pictures of thermistors on page 7. I don't have pictures of them. I'm just being honest, I have not used thermistors a lot. Mostly, pretty much everything I've ever messed with is RTDs and thermocouples, but I know thermistors are out there. Nothing on the rest of page 6 or 7 for infrared pyrometers. Anybody know what an infrared pyrometer is? Everybody knows what that is? That's an infrared pyrometer. So everybody's seen one of those. Everybody got scanned at 87 degrees whenever they're during COVID going in places and stuff like that.
I wouldn't let them scan.
Wouldn't let you-
I heard something about it, like, the infrared signal's not good to point directly at your head or something like that, so I just wouldn't let them.
I don't know. They're not, to me, every time they scanned my head, it was never anywhere close to 98.6. Like, they were like, as long as I was below 100, they're like, okay. They would scan me at like 92. I'd be dead. I don't know. But these are huge in industry. Because you can use them, flipping over to page 8, you can use them for different stuff. You could shoot them at bearings on motors and stuff like that, but the big thing is if you had pipes running overhead, and you had say you had a control valve up there and you didn't know if it was, like the computer screen shows it opening and closing, but your troubleshooting technique is telling you that like something goofy's happening with it, you can take one of these infrared guns and you can shoot the pipe on either side, and if they're equal in temperature, then you know the valve's open, right? If they're a little bit different in temperature, then you're going to be able to tell, more often than not, be able to tell the valve's closed or something like that. So very useful as far as temperature and stuff like that. On page 8, I've got figure 8 and figure 9 both highlighted as online test questions. Separate questions. In figure 8, I don't know that they show you the thermistor system. The question is going to be, if you want to write it on there, what type of device uses this graph? You just need to know that that's the thermistor for figure 8. I don't think they're going to have the thermistor symbol on there, but just know that that graph is used for thermistors, and then that is an IR gun. They're going to show a picture of that, and you know that that's an IR gun. Take a minute and answer the 3 questions on page 10.
Bless you.
Keep on going in section 2. Measuring pressure. The trade terms in this, you're going to need to know. Absolute pressure is going to be the pressure exerted in all directions by the atmosphere equals gauge pressure plus atmospheric pressure. Anybody remember what pressure is at sea level?
14.7.
Sounds right. Yeah, I think that's right. So where we all currently live, like atmospheric pressure should be somewhere around that, where we are at sea level. The differential pressure is going to be important just because that's how differential pressure transducers work. I know the next day in the lab you guys are going to be doing that with that differential pressure meter. I do have the pressure one highlighted. The amount of force exerted on a substance over a given unit of area. You know what just basic pressure is. I do have the first equation, the bottom left of page 11 highlighted. Pressure equals force over area. Units of pressure measurement. Most everybody is familiar with PSI. Then I know we've talked about bars a little bit. A lot of instrumentation equipment uses inches of water as their medium for measuring pressure. So that's important. You're gonna, like inches of water or inches of water in a water column is a way of measuring pressure. I have where you see the blue highlighted gauge pressure through the end of that paragraph highlighted. Gauge pressure is measured and expressed as pounds per square inch gauge or PSIG or kilopascals gauge, kPa gauge, and considers the presence of atmospheric pressure. For gauge pressure, the gauge starting point of 0 PSIG actually begins at atmospheric pressure level. So what they're saying, then my next highlight is that next equation. PSIA is equal to PSIG plus atmospheric pressure. So if you want to find absolute pressure is equal to gauge pressure plus absolute pressure is equal to gauge pressure plus atmospheric pressure. Right together? Huh? I forgot all about y'all having tests.
We got 2 tests.
Yeah,
We have 2 tests.
I figured you weren't going to.
I thought we were gonna go over it.
Yeah.
Did we go over it?